Hello students, in this lesson we shall study about the packing efficiency in crystals. Before I start, I request you to subscribe the channel so that you get all the notifications of my videos. And I will also request you to see the video till the end of the video so that you don't miss anything important for your examination point of view. So friends, let us start our video. The topic is packing efficiency in crystals. This is a part of your chapter solids in your NCERT book. So let us first see that what is packing efficiency in crystals. It is the efficiency of constituent particles. Percentage, it is given in percentage, and it is the volume occupied by the constituent particles in a unit cell. So it is given by percentage of space occupied by constituent particles in a crystal, and it is defined as the packing efficiency of a crystal. If more empty space is there in the crystal, then we say that a packing efficiency is less. And if empty space is less, we will say that the space is utilized in maximum manner, in more effective manner, and we will say that packing efficiency is more, it is good. So it is calculated as percentage volume occupied in a unit cell, and its formula is volume occupied by the constituent particles divided by total volume of the unit cell into 100, and it is calculated as percentage. Now we will derive packing efficiency of some of the structures, crystalline structures. First of all, we will see that what is the packing efficiency in simple cubic lattice. Here atoms are located at corners. There are 8 corners and 8 atoms are present. But effective number of atoms is 8 into 1 by 8 is equal to 1. Why? Because all the atoms which are present at the corners, they are shared by the adjacent unit cells. And there are 8 adjacent unit cells which share the 8 atoms. So the effective number of atom which is shared by one unit cell is 8 into 1 by 8 is equal to 1. Now I think it is clear that why the number of atom is taken as 1. So packing efficiency of simple cubic lattice will be volume of one atom divided by volume of unit cell into volume of unit cell means if it is A, then volume of cube, it is A, all the edges are A, then volume will be A cube, and A is equal to this R plus R. R is the radius of atom, because 2 atoms are there, so R plus R, A is equal to 2R. And volume of one atom is formula 4 by 3 pi R cube. This is the formula for volume of spherical bodies. Since atom is spherical, then we say that its volume is 4 by 3 pi R cube. And volume of a unit cell, is A cube. Now if we calculate it further, it will be 4 by 3 pi r cube. A cube, A is equal to 2r. 2r cube into 100. Here also into 100. This will be equal to 4 by 3 into 22 by 7. Value of pi is equal to 22 by 7 into r cube divided by 8r cube into 100. If we calculate it further, it will come out to be 52.4%. So this is the packing efficiency in simple cubic lattice. Now we shall further calculate what is the packing efficiency in a body-centered cubic structure, BCC. It is BCC. In body-centered cubic structure, 8 atoms are present at 8 corners and 1 atom at the center of diagonal of the body. Means if we draw a cube here, then we name it A, B, C, D and E, F, G, H. Then 8 atoms are present at all the corners, all the 8 corners, and if this is CE, CE is diagonal of body. So at the center of CE, one atom is present. One atom is present at the diagonal of the body. So if we see, this is, if we take, so what will be the effective number of atoms? One atom is shared by this, which is present at the diagonal, that is shared by this unit cell, one atom, and 8 atoms at 8 corners are shared by 8 unit cells, so it is effective is 1. So 1 plus 1, that is 2 atoms are, effective number of atoms are 2 atoms. And now we draw another, this is, we take triangle EAB, this EAB. Here angle A is 90 degree. This is perpendicular triangle. So by Pythagoras theorem, B square, this is B. If we take it B, then B square is equal to A square plus A square. And B is equal to 2A square. B is equal to under root 2A. Now we take another triangle CE, BCE. That is, here we draw an BCE. Here CE is the diagonal of the body, CE. For simplicity, we have drawn this triangle outside so that we can understand it clearly. So at the CE, at the center of the diagonal, there is one atom present which is shared by only this unit cell, and 2 atoms are present at the C and E. Here it is R, here it is 2R, here it is R. So this side, which is taken as C, represented by C, we say that C is equal to 4R, and here it is BE is B, here BE is B, which is under root 2A, and this is BC is A. Then we say that C square is equal to A square plus B square, which is equal to A square plus B square is equal to 2A square. Then C square is equal to 3A square, and C is equal to 4R, and C square is equal to 3A square. By this we calculate C is equal to under root 3A, and 4R, by these two equations we get 4R is equal to under root 3A, and by this A is equal to 4R by under root 3, and R is equal to under root 3 by 4A. Now we calculate, we have seen that packing number of effective number of atoms are 1 plus 1 is equal to 2 atoms. Now packing efficiency in BCC structure will be volume of effective atoms present in the unit cell, and that are 2 atoms, divided by volume of unit cell into 100. So it is 4 by 3 into pi r cube. 2 atoms are there, so it is multiplied by 2 atoms, divided by 4R by under root 3. This is A. Volume of unit cell is cubic structure. The volume will be A cube, and A is equal to 4R by under root 3. We have taken A cube here. So if we calculate it further, we will get, by cutting all these R cube and R cube will be in denominator and numerator will cut each other, and if we calculate this expression, we will get into 100. We will get it is 68%. So the packing efficiency in BCC structure is 68%. See, in simple cubic lattice it was 52.4%, and in BCC body centered cubic structure it is 68%. Now we will see that what is packing efficiency in cubic closed packing, CCP. See, in CCP and in HCP, hexagonal closed packing, the efficiency is same, but for simplicity we will first derive the packing efficiency of CCP, cubic closed packing. In CCP, the 8 atoms are present at the 8 corners, and one atom each at the faces. Each face, there are 6 faces, so there are 6 atoms, but these atoms, each atom is shared by 2 adjacent unit cells. So what will be the effective unit? It will be here 6 faces, the 6 atoms which are present at 6 faces. The effective number of atoms is 6 into 1 by 2, because each of the atom is shared by 2 adjacent unit cells. So this will be 3. And effective number of atoms which are present in cubic closed packing, 8 atoms gives 1 atom, 1 effective atom, and 6 diagonal atoms, they give 3 effective atoms. So in all it is 4 atoms which are effectively present in cubic closed packing. Now we see, we take this A, B, C, D, E, F, G, H. So for simplicity, we take another figure here, because they are present here, and at each, if we draw a diagonal, at each face there is 1 atom. So if we draw another this triangle ABD outside for clarification, ABD, and if we get 1 atom at face, 2 atoms at the corners, then it is 2R, it is R, this is R, and this is A, this is A. Now take the screenshot and we will calculate how the efficiency in cubic closed packing will be calculated. See, the figure was like this. A, B, D. Here it is 2R, R, R. So this is A, and this is diagonal of the face was B. So by Pythagoras theorem, B square is equal to A square plus A square is equal to 2A square, and B will be equal to under root 2A. So, and also B is equal to 4R. This B, 2R plus 1R plus 1R, 4R. This is equal to 4R. So we say that A is equal to 4R by under root 2R, we said 2 by 2. This is, and R is equal to, it implies that R is equal to A by 2 under root 2. Now we will calculate. We have seen that effective number of atoms, they are 3 plus 1, 4 atoms. So the effective number of atoms, that is equal to 4. Now how the packing efficiency will be calculated? It will be volume of 4 atoms divided by volume of unit cell into 100, and volume of 4 atoms will be 4 into 4 by 3 pi r cube, and volume of unit cell is A cube. A is this 2 by under root 2 r whole cube. And if we calculate it further, we will get that this packing efficiency in CCP is 74%. It is 74%. So now we compare the packing efficiency of all the 3 structures. See, packing efficiency in simple cubic, it is 52.4%, and in body centered cubic structure, it is 68%, and in cubic close packing structure, it is 74%. Now we see that simple cubic lattice, in simple cubic lattice, it is 52.4%. Body centered cubic, it is 68%, and for cubic close packing, it is 74%, and for hexagonal close packing also, it is 74%. Now, if we see that effective number of atoms in a unit cell, see in simple cubic lattice, the effective number of atoms were only 1, and for body centered cubic, it was 2, and for CCP, it was 4. So, more is the effective number of atoms in a unit cell, the more will be the packing efficiency of the unit cell of a crystal. So, now we come to the end of this video, and I will again request you to please subscribe